So welcome to Analog Microelectronic Circuits lecture. This today we'll start our unit 2. So this is unit 2 and the lecture 1. So this unit, the second unit is all about bipolar junction transistor. So we will start with bipolar junction transistor. So in the previous unit, if you remember, we were discussing about MOSFETs, and in the first class or even when we start, before we start MOSFET, we discussed about three terminal devices. So the main idea of the three terminal devices, we can actually have some control between control over the current that is flowing between the other two terminals, right? So so if you look at history, we will know that the device which has come first is BJT. That happened, yeah. So BJT, can I get a response in the chat box, like when was this BJT invented and where? Can I get some response? Yeah, it is in Bell Labs. Yes, in 1947, 1948. Yes. So BJT in 1947 or 48 in Bell Labs, and that actually, or the invention of this BJT or bipolar junction transistor has revolutionized electronics industry like anything, because till then what we had was vacuum tubes. And if you remember, the ENIAC, the first electronic computer, then was made of vacuum tubes, and the size of that ENIAC or the personal computer was so huge. And when we say vacuum tube, it is not a semiconductor device that works on the principle of something called as thermionic emission. That is also control using a control grid. They could actually control the flow between these anode and cathode. But bipolar junction transistor is the first semiconductor. It is a semiconductor device, and that too that is having ability to actually control the current flow between two. But if you look at history, you will also understand that the idea of MOSFET, or the principle and the operation of MOSFET or field effect transistors, were well explained in 1930 by a person called as Lilienfeld. But then, because of lack of fabrication methods, because of lack of purification methods of silicon, or the purification methods, he could not actually fabricate a field effect transistor. And later, after this invention of BJT only, the first field effect transistor was also done. It is by the same Bell Labs only, but it happened after this bipolar junction transistor. And so for that reason, transistors, especially BJTs, are considered as, or this device has revolutionized electronic industry from then. And later MOSFET took over because of the because of the ease in fabrication process. But still, in today's ICs also, we are using BJT, especially in high frequencies, right? So yeah, just to brief what all things I was sharing with you people. So BJT is also the main use, or BJT was also used uh, as an amplifier. So why I'm calling it is also used, because we already discussed amplifiers based on MOSFETs. Now this MOSFET has the MOSFET became popular in early 2000s, or well after BJT only this MOSFET became popular. And then only we say something called as a CMOS technology. The CMOS technology that led to this ICs and all those revolution that happened in the IC industry, right? So, but if you look back to BJT, even today in analog circuits, we use BJTs for various reasons. Especially we use in RF circuits also, in wireless applications, right? So BJT find application even today. Now, since we spoke about this one BJT, um, I just want to tell you something called as BiCMOS. Have you heard about BiCMOS? BiCMOS. Can I get some response? Heard about BiCMOS? No, all right. Okay, so BiCMOS is actually a combination, or this BiCMOS combines the features of both technologies. So when I say both technology, one is BJT and the other one is CMOS. So we call it as BiCMOS. So now to just list out the things or list out the features of this BiCMOS, it is low power compared to other. Then it has high input impedance. These are some of the features. Right. So these are actually the features of CMOS. Low power and high input impedance are the features of CMOS or MOSFET. Now, if we look at the features of bipolar junction transistor, they have high frequency. They can operate actually very high frequency. Now you'll be wondering why BJT can operate at high frequency, not MOSFET. We'll see in terms of unity gain frequency, another parameter. Then it has high current driving capability. This also we will see very shortly. So these are some of the features of both BJT and MOSFET. So when you say BiCMOS, this is often seen in some of the ICs where they combine the features of both bipolar junction transistor and MOSFET and has come up with something called as BiCMOS technology. Right. So, but anyway, for our discussion, especially for Unit 2, we will be discussing only on BJT or bipolar junction transistor. So let me ask you one question. Why BJT? So why BJT is known as bipolar? Can I get some response in chat box? Why it is called as bipolar? Why bipolar? All right, two poles cannot be interchanged. Which are the two poles? Current conduction is due to both electrons and holes. Yes. Oh, Kiran, yeah, you have mentioned something that is true, but source and drain corresponding to MOSFET, right? Source and drain is corresponding to MOSFET. So, yeah, Kiran, that is true, whatever you told. BJT is not a symmetrical device, but MOSFET is a symmetrical device. So, what is the meaning of that? When you say MOSFET, MOSFET is a symmetrical device where actually you can interchange between the source and drain terminals. Source and drain terminals can be interchanged, but that is not possible in BJT. That means none of the terminals or emitter and collector of BJT cannot be interchanged because basically BJT is not a symmetrical device. So we will see that, but the reason why we call it as bipolar is the current conduction in a BJT current conduction in BJT is because of both charge carriers. So when I say both charge carriers, it is both electrons and holes. Right. Yeah. So as others were mentioning, both majority and minority charge carriers are responsible for the conduction of current. Very good. Current is due to two types of charge carriers. Yes, Nilanjan, it is bipolar because it contains both N type and P type semiconductor. Okay, so yeah, to make it very clear, it is not because when you have two types of materials, definitely there can be a possibility of two types of charge carriers, right? Electrons and holes. That is true with the same in the case of MOSFET also. There also we have two types of materials, but In a MOSFET, the current conduction is because of only one type of carrier, because the current is between source and drain, which are of the same type, and that is controlled by gate, which is isolated, but the current flows through a channel which is also of the same type, right? So there only majority, we'll say that it is a unipolar device. MOSFET is a unipolar device, but BJT, the reason is we have two types of charge carriers. That is the reason why we call it as bipolar. So unipolar is actually MOSFET because current conduction is either due to electrons or due to holes. It is or, but here it is both, right? So this is just an introduction for B. I hope Nilanjan it is clear, and for everyone for the response, yeah, thank you for the responses, right? now, now if you look at yeah, so I'll just come down. So in this unit 2, we will be discussing about the device structure. So let me ask you one thing, whether this red is okay and whether my writing is very small. Is it manageable for the day?
Yes.
Okay, okay, yeah. So we will definitely look at the device structure just to have a look on PNP and NPN transistors. Probably these things you would have already covered in your basic electronics, but still we will review it. Second is we will look at the physical operation. Device, the first is structure as in the case of MOSFET. Then we will look at the operation. Then that will be followed by characteristics. So characteristics means IV cara. So in this case we will specifically call it as input and output cara. But that was not true, or that we did not mention this way in the case of MOSFET, because there the input current itself was 0. So we did not, we called it as output characteristics or drain characteristics, and the other one is called as transfer characteristics. But in the case of BJT, we will call it as input and output cara itself. So once we have understood the characteristics, then we will look for DC biasing, right? So once we are done with biasing, then we will go for small signal models. I hope you can appreciate the flow what we are doing. So once we are done with MOSFET, right? We'll start with structure, operation, cara, then DC biasing, then small signal model, and finally we will go for amplifier configurations. So one difference is we have taken long time to cover MOSFET. It was around 20 lectures, but the BGT, I think we will take only half of the time because many things we can compare and we can move forward, right? All right. So I think there is no, there will not be any doubts from this. If at all it's there, you can ask me. I'll clarify. Now, let us just start with the device structure. So in today's class, we will briefly look at device structure, and then we will see some DC problems today. Right. So we know that if you look at the device structure, there are three regions. There will be three regions. One is emitter, other one is called as base, and the third region is called as collector for the specific reasons. Now, so since there are three regions, we can identify two PN junctions in this. So either the structure is of NPN or it is of the structure of PNP. That means you can see two junctions, two PN junctions. Since you have two PN junctions, you can bias the two PN junctions in two different ways. So each PN junction can be biased in two different ways. That means altogether how many combinations are possible? So we know that a single PN junction can be biased in two ways, right? What are the two ways? I can bias a PN junction as in forward bias as well as in reverse bias. Yeah. So a single PN junction, I have two possibilities. So since you have two PN junctions, we have four possibilities, or we can actually have four different ways of biasing this PN junction, right? So one is, so let me draw the structure first. This is the structure where we partition it into three. This region we call it as emitter. This is called base. This is called as collector. Now we will take terminals from all the three regions. So this is emitter region. Now this is base region, and another terminal is taken from the collector region. All are semiconductor regions. The only difference is it will be either NPN or it will be PNP. Right. So from the structure itself, I have made a difference in the in emitter, base, and collector to make it very clear that we cannot interchange any of the regions in a BJT. Right. So now I can see there are two junctions possible. There are two junctions, right? Emitter based junction and collector based junction. Very important. So two PN junction. One is called as emitter based junction. And other one is called as collector based junction. So I can bias both junctions in two ways. That means four combinations are possible. So let me list out the combinations. So this is emitter based junction. This is collector based junction. Now I can bias both junctions as forward bias. So I can bias both emitter based junction and collector based junction as forward bias. Can you tell me what will be the mode then if I bias both emitter base and collector base as forward? What we call this mode? Any idea? So I'll just list out the possibilities. I can make this reverse bias. Then I can make this reverse bias and this also reverse bias, and finally I can make it as reverse bias, and this can be. These are the four possibilities, right? Yes, saturation. So when we keep both junctions in forward bias, we call it in saturation region. When one in forward and another one in reverse, we call it as active mode. When both are reverse, it is very clear that both will be off, so I can call this as cutoff. And when emitter base is reverse and collector base is forward, that is just opposite of this active region, we call this as inverse active region, inverse active mode. So these are the two junction and this is the mode. Now if you look for application, yeah, I'm seeing the response. So both junctions are forward bias. Then so Jessica, can you tell me how I can use this BJT in all these four different modes? Jessica, are you there? Hello, Jessica. Yeah, Jessica. So can you just tell me how we can use this transistor in different modes? What way we will relate? Are you getting my question? Hello, Jessica. All right, I think there is some disturbance there. All right, Joel.
Yes, sir.
Yes, Joel. So can you identify the different regions and the way we can use it?
So in cutoff region, we can use it as a switch.
Okay, so when you say switch, it is an open switch or a closed switch?
Closed switch.
Okay, so if I want to use something as a switch, there are two modes, right? One should be open and one should be closed. So how will you say in cutoff region we can use it as a closed switch? When you say closed switch, current will
So
flow through
open
that.
switch, sir. Open switch. Open switch.
Okay. In cutoff it
Current
will
will
flow
not
through.
flow.
Okay, and
In active region, it acts as an amplifier.
very good. So where it will act as a closed switch?
Saturation region.
Very good. Yes. Thank you, Joel. Yeah.
Uh,
Now, in the last one, when one is reverse and other is forward, generally that mode is not used. But still, if you are trying to use it, it may act as an attenuator because other mode is amplifier. It may act as an attenuator. Right. So these are the various modes. Now, before going to the details, so we will look at. We have just seen the device structure. So before looking at device operation and other things, I just want to give you a few some numericals. Numericals in the sense where you can actually apply KCL, KVL, and find the operating point. Right. So I just want to check how far you are comfortable with these kind of things. So by the way, this is a symbol of BJT. I think you are familiar with this. So this is 6 volt, this is 1.5 volt, this is 820 ohms, this is 680 kilo ohms. The beta of this is 500. Now the intention of giving the circuit is not to find the operation of this because we are still we are yet to discuss that. But what I want you guys is to find the base current, find the collector current, and also find the VC voltage. Can you guys try out? So assume that this is a silicon transistor. Try the question, no need to post answers. I'll ask and then only you can post the answers. I want all of you to try. We will see, definitely we will see these kind of numericals afar. This is just I want to check with you what all things you have done from your basic electronics.
Sir, is that 820K or 820 ohm?
820 ohms.
Okay, sir.
Yeah, so if you guys tried, can you post answers or let me just wait, do not post now. Pooja, are you there? Pooja? Pooja, are you there? Okay, so Pooja, can you unmute for some time?
Yes, sir.
Yes, Pooja. So did you get the answer for this question?
No, sir, I'm trying it.
Okay, okay, yeah, please do it. Meher? Yes, Meher. So Meher, did you get the answer for this?
Sir, no, sir.
No. Oh, okay, okay. So those who are getting answers, you can put in the chat box. You can just try, and whatever answers you are getting you can put. It is not like mandatory that you should know how to solve this. I just want to know how you guys get this. Okay. So have you come across these kind of numericals in your first semester? Can I get response as yes or no? Or you have come across these kind of, okay, all right, yeah. So this is a small check on those things. So I saw the answers posted by Manikandan, Pradyumna. Yeah, there is a small correction over there. I'll clarify that. Okay, yeah. So any more responses? Okay. So coming to this question, yeah, we will see the operation and we'll understand that. But to solve these kind of questions, what we generally do is it is given that the device is silicon, right? Now, if the device is silicon, then we know that if a PN junction is forward biased, then what will be the voltage across that PN junction? If it is a silicon PN junction, we consider it as 0.7, right? So now you can see this is emitter, this is base, and this is collector, and the two junctions will be biased. So one is emitter base junction and other is collector base junction, right? The first thing is we will try to see how the junctions are biased. So this is N is N, right? So this is N, this is P, and this is N, right? Now so your emitter is connected to 1.5, base is connected to 6 volt through a 680k resistance, right? So more likely this PN junction, since the base is connected to a higher voltage of 6 through 680k and emitter is connected to 1.5, which is a less voltage, so we can say that this emitter base junction is forward biased. Similarly, if you look at collector base junction, so what is collector? Collector is an actually N, and collector is connected to 6 volt through 820 ohms resistor. Base is V, that is also connected to a 6 volt, but that is through a 680k resistance. So if you look at the junction condition here, the chance is that this collector base junction will be reverse biased. Why it is reverse biased? Because collector is actually an N which is connected to a higher positive, because the resistance connected here 820 ohm, or the other case it is 680k, right? So the chance, so the possibility is something like this: emitter base junction is forward biased and collector base junction will be reverse biased. Now, if your emitter base junction is forward biased, what will be the voltage across this emitter base junction if it is a silicon diode? If it is a silicon PN junction, any can I get some? Yes, Nilanjan, I saw your answer.
0.7.
Yeah, Parnika, I saw your answer. Yes, Pradyumna. Yeah. So I'm discussing that itself. Yeah, it is 0.7. So this, so how will I mark that? 0.7 is actually between these two terminals. So this is 0.7. Right. Now, if I want to find IB is actually base current. So how will be the current flow in this? In a BJT, in a NPN BJT, emitter is the terminal where current flows out, and this current will be coming in, and this current is also will be coming in. Right. So if I mark this as IB and this as IC, I can find IB if I know this voltage and this voltage. I know the voltage at this end, which is 6. So I can write IB as 6 minus, what is base voltage? I need to find what is base voltage. So IB is equal to 6 minus base voltages. At emitter I have 1.5. Now from there I have 0.7 more at base. Right. So 1.5 plus 0.7, which is equal to 2.2, that is actually your base voltage. So 6 minus 2.2 divided by 6K, 680K will give you the base current value. So now if you check base current value, you will get an answer. You can try that now. Now if you know base current, you can find collector current. That is by the simple relation beta into IB. So we will be definitely looking at these relations and the current equations, everything from tomorrow's class. This is just, I want to know how far you are familiar with these kind of DC problems. So you can find what is IC, that you can try out. Once that is done, if you want to find VCE, VCE is actually the voltage between this collector and emitter. Emitter voltage, I know it is 1.5. Now the only thing is you want to find collector voltage. So how will you find collector voltage? VC can be obtained as 6 voltage minus the collector current into 820 ohms. That you will get VC. Now you can find VCE. How will you find VCE? VCE is VC minus VE. So now can you get all the answers? Find out one by one and please post in the chat box. Mohan, can you check once again what was your VC? Pradimna, VC is 2.2, right? That is right, Pradimna. Yes. Yes, Bhavana, it is 2.2. Any more answers? So can I? Yes, Ershad, it is not minus. How come you got a minus sign? Okay, so what is IB? What is the value for IB? So can one, yeah, IB is 5.58 microamps. That is right. So IC will be not milliamps, Irshad, it is micro. Yeah. IC is 2.79 milliamps. So with that you will get VC. VC is 709 volts, and that minus 1.5 you will give you 2.209. Yes. Right. So if you have doubts in this, so let me cross check with. So Pooja, now did you get it now? You understood this? Okay. Okay. Yeah. So Meher is there?
Yes, sir.
Yes,
Answer.
Meher. Okay. Okay. Very good. Okay. So can I give you one more question of this type? Even though the intention of this is just to check whether you are comfortable, I'll give you one more question. This will be a little tough for you. This is given as 6. Beta is given as 35. VCE is given as 3 volts and IC is given as 0.5 milliamps. Yeah, so the question is to find the value of RB and RC. Find the value of RB and RC. Just give a try. After looking at the operation of BJT and the current equation, we will come back to these kind of problems when we start with the DC analysis. Yeah, so any answers? What is RB and what is RC? RC is 6K. Yes, yes, Kirtana, right. Karthika, yes, that is right. Ashwit, yes, RC is 6K and RB is okay. Can you check for RB? Okay, it's slightly different. Probably the value what you have approximated for IB matters. RB you will get 370K. Yes, that is right. Ashwit, can you check the value for RB? Are you getting is yes, Nilanjan, it's right. 6K and 370K. Very good. Yes. RB is 370K, 371. Yes. Oh, very good. So how will you solve? So others who could not solve this, you can just take it from me now. IC is given, so you can directly find IB. So IB is nothing but IC by beta, right? So those who are wondering what is this relation of IB and IC, that also we'll see shortly. So that you will get as 14.1 some 28 microamps. That will be your IB. Now once IB is known, IB is actually the current flowing like this. If that is known, and we know that if this is forward bias, this will be 0.7. So I can find RB. RB is 6 minus 0.7 divided by this IB value. That will give you 370K. Now VCE is known and IC is known, so you can definitely find RC. RC is 6 minus VCE, which is 3 divided by IC, which is 0.5. 3 by 0.5, it is 6 kilo ohms. This is your RC, right? So this is how we solve DC problems. Now we should be careful on the polarity when we do with NPN and PNP BJTs. That's all, right? So today's class I am winding up here. We'll continue from the operation of BJT from tomorrow.